Section: Introduction. In this section, we introduce an emerging class of reasoning language models that enhance their performance by extending their thought processes during complex problem solving. However, these models face a significant challenge. Their reasoning length is uncontrolled, which prevents us from effectively managing the compute resources needed to achieve desired performance levels. Sometimes, the reasoning sequences can become excessively long, wasting compute, while in other instances, the models may stop prematurely on difficult problems. Recent approaches, like S1, attempt to manage this length by requiring the model to generate specific tokens when the output is too short or too long. Unfortunately, this method can hinder performance compared to the model's capabilities. Other research has looked into controlling output lengths in various domains, but reasoning models encounter unique challenges, such as needing to balance longer outputs with computational costs. To address this, we propose length-controlled policy optimization, LCPO, a straightforward reinforcement learning method that provides precise and adaptable length control for reasoning language models. LCPO trains models to achieve two goals: ensuring the final output is correct and generating reasoning sequences that adhere to specified length constraints. This approach allows models to meet length requirements while enhancing reasoning performance, rather than relying on rigid, predefined rules. We explore two practical constraints: LCPO exact, which demands the reasoning to match a target length exactly, and LCPO max, which limits the output to a maximum length. We apply LCPO to fine-tune a 1.5 billion parameter reasoning model, resulting in L1 max and L1 exact. Our L1 models can effectively balance token usage and reasoning quality, adjusting between shorter, efficient reasoning and longer, more accurate outputs based on different length prompts. Notably, 1 point on this balance recovers the original model's performance while surpassing S1 across all reasoning lengths. In math reasoning tasks, L1 outperforms S1 by up to 100% relative and 20% absolute under the same conditions. Beyond math reasoning, we find that LCPO-trained models generalize well to other tasks, including logical reasoning and general knowledge benchmarks like MMLU. Additionally, models trained with LCPO that excel at long reasoning can also perform remarkably well at short reasoning tasks, showing significant improvements over their original versions, even at the same output length. We demonstrate that a 1.5 billion parameter model can match the performance of GPT-4o while using the same token budget. In summary, we present length-controlled policy optimization, LCPO, as the first reinforcement learning method for training reasoning language models to produce outputs that meet user-defined length constraints. We show that L1 achieves high length control and state-of-the-art reasoning accuracy on challenging math benchmarks, and that this length control extends to various out-of-distribution tasks. Our LCPO-trained models also outperform larger models like GPT-4o while maintaining the same token budget. Section Summary. In this section, we introduce Length-Controlled Policy Optimization, LCPO, a reinforcement learning-based method that enables reasoning language models to generate outputs with precise length control while optimizing performance. Our experiments show that LCPO-trained models can effectively balance reasoning length and accuracy, outperforming existing methods and generalizing well to various tasks, including math and logical reasoning. Section: Method. In this section, we address the limitations of current reasoning language models, which do not allow us to control the length of their generated reasoning outputs. This lack of control makes it difficult for users and applications to adjust the inference compute budget based on specific task needs or available resources. To tackle this issue, we condition our model on a target token length specified in the prompt. Specifically, given an input prompt and a target length, we aim for the model to generate a response whose length is as close as possible to the target while still providing the correct answer. This approach links accuracy with output length, ensuring that the reasoning aligns with user-defined constraints. We start with a pre-trained reasoning language model and a dataset containing input prompts and their corresponding answers. To enable length control, we enhance each prompt by adding a target length instruction. This creates a new dataset where each prompt includes a directive to think for a specified number of tokens. We then update our model using a reinforcement learning approach, specifically employing a method called GRPO. Our reward function consists of two components, a correctness reward and a length penalty. This function encourages the model to produce correct answers while also favoring concise reasoning when shorter outputs are requested. We refer to this model as L1 exact, and during inference, we control the output length by appending a fixed target length to each test prompt. Additionally, we develop a variant called L1 max, which allows for flexible output lengths while adhering to a maximum length constraint. This is useful when users prefer to stay within a computational budget rather than generating outputs of exact lengths. We fine-tune the L1 exact model using a modified reward function that gradually penalizes outputs exceeding the target length, encouraging the model to use fewer tokens when possible without compromising correctness. For our experiments, we train on the DeepScale R preview dataset, which includes 40,000 question-answer pairs from various mathematics sources. We evaluate our models on several reasoning datasets. Our base model is a 1.5 billion parameter model that has been fine-tuned on this dataset. Due to computational limits, we restrict the maximum context length during training and evaluation. We further fine-tune the model with the LCPO exact objective, resulting in the L1 exact model, and then with the L1 max objective to create the L1 max model. Section Summary. In this section, we address the limitation of current reasoning language models in controlling the length of generated outputs by conditioning them on a target token length specified in the prompt. We introduce two models, L1 exact and L1 max, which utilize reinforcement learning to optimize for both correctness and adherence to length constraints, allowing for flexible output generation while respecting computational budgets. Section: Baselines. In this section, we evaluate our proposed method against several baseline models. We refer to the first model, DeepSeek R1 Distill Quen 1.5b, as DeepSeek R1 to 1.5b. This is the SFT version of QWEN 2.5 to 1.5b, fine-tuned on reasoning traces from DeepSeek's R1 model. The second model, DEEPSCALER 1.5b Preview, is the original model assessed without any modifications for length control, which we call Agentica 24K. The third model, DEEPSCALER 1.5b Preview 4K, is a version of AGENTICA 24K fine-tuned for a context length of 4K tokens, allowing for a fair comparison to our method, which we refer to as Agentica 4K. The fourth model, S1, is a budget forcing method that controls reasoning length through simple interventions, implemented on the AGENTICA 24K model. For our evaluation, we look at two main aspects. First, we measure how well the model meets the target length by calculating the average difference between the generated token length and the target length. Second, we assess the overall performance, or problem-solving accuracy, at various target lengths, specifically 512, 1024, 2048, and 3600 tokens. Regarding hyperparameters and implementation, we use the same settings as in DEEPSCALER 1.5b Preview, with a learning rate of 1 millionth and a batch size of 128. The maximum context length during training is set to 4K tokens, which we extend to 8K tokens during evaluation. We train for 700 steps using the Virl framework, sampling target lengths uniformly between 100 and 4,000 tokens. The balancing parameter in our reward function is fixed at 0.0003. We note that we did not perform extensive hyperparameter tuning, so there is potential for further improvements. In our results and analysis, we demonstrate the effectiveness of our method, LCPO, across various settings and benchmarks. We evaluate its performance, generalization on out-of-domain tasks, ability to control length constraints, and competitive performance in short chain-of-thought setups. Our findings show that L1 significantly outperforms other length-controlled models while maintaining strong performance. We compare the performance of L1 Exact and L1 Max with other baselines across different generation lengths. Both L1 variants excel across all token budgets while ensuring precise length control. Compared to S1, which is also designed for length control, L1 shows impressive improvements, achieving over 100 to 150% relative and 20 to 25% absolute performance gains at 512 and 1024 token budgets. This difference arises from two main factors. L1 adapts its reasoning to fit within length constraints without interrupting the thought process, while S1 often truncates reasoning. Additionally, L1 is trained to produce high-quality reasoning chains of varying lengths, effectively learning from longer chains to create shorter ones. We observe a log linear scaling pattern with L1, similar to previous works by OpenAI, where performance improves linearly with the log length of reasoning chains. However, L1's scaling curve has a smaller slope, indicating better effectiveness at lower token ranges. L1 Exact performs about 1% below AGENTICA 4K, which is the same model as L1 but trained without length constraints. This difference is mainly seen in the AMI dataset, where unconstrained models can generate longer chains for complex problems. L1 Exact uses the same token budget for all problems, which may lead to extra tokens being spent on simpler tasks. L1 Max addresses this issue by optimizing token usage based on problem difficulty while adhering to the upper limit, often outperforming L1 Exact with up to half the tokens used. L1 Max is particularly useful when exact token counts are less critical than managing compute budgets. Finally, our scaling trends suggest that with longer context training, L1 could match or even exceed the performance of AGENTICA 24K while maintaining strong length control. Section Summary. In this section, we evaluate our proposed method against several baselines, including DeepSeek R1 to 1.5b and Agentica models, focusing on their ability to control output length and problem-solving accuracy across various token budgets. Our results demonstrate that our method, L1, significantly outperforms other length-controlled models, achieving superior performance while maintaining precise length control, particularly excelling in adapting reasoning within specified constraints. Section. L1 generalizes effectively to out-of-domain (OOD) tasks. In this section, we evaluate how well L1 generalizes to tasks outside its training domain. We categorize out-of-domain datasets, including GPQA and LSAT, which are similar to what L1 was trained on, and MMLU, which is likely outside its training range. Our findings show that L1 performs well in these new domains, with its performance improving as we increase the token budget, often matching benchmarks set by AGENTICA 4K, even with length control constraints. For GPQA and LSAT, we see a consistent performance trend similar to our main datasets, while MMLU shows a weaker linear relationship, likely due to its focus on knowledge rather than extended reasoning. We also assess L1's ability to adhere to length constraints across various mathematical reasoning datasets. Our results indicate that L1 maintains good control over output lengths across different token budgets, with average deviations from target lengths being low, around 3%. Although out-of-domain datasets show higher errors, they are still preferable to uncontrolled prompting. Further analysis reveals that larger errors tend to occur at higher token budgets, particularly in tasks like MMLU, where longer reasoning is often unnecessary. We note that these errors can be significantly reduced with additional reinforcement learning training. Next, we compare L1's performance at lower token budgets to that of its base non-reasoning model and larger models like GPT-4o and LLaMA 3.3 to 70b. Our results show that L1 consistently outperforms or matches these models across all datasets, achieving an average of 5% better performance than its non-reasoning counterpart and 2% better than GPT-4o. This is significant, as it demonstrates that a 1.5 billion parameter model can outperform leading models at the same generation length. Overall, our results suggest that with appropriate reinforcement learning training, long chain of thought models can effectively function as short chain of thought models while outperforming their base versions. Finally, we analyze how L1 adjusts its reasoning strategies based on token budgets. We examine the frequency of reasoning-related terms in outputs of different lengths, revealing shifts in reasoning patterns. We categorize these terms into 4 patterns: self-correction and verification, exploration and alternatives, context setting, and conclusion drawing. Our analysis shows that self-correction and conclusion drawing terms increase significantly in longer outputs, while exploration-related terms generally decrease. This indicates that shorter chains of thought focus more on self-verification and conclusions, while longer outputs maintain a stable ratio of thinking tokens to solution tokens, suggesting that L1 efficiently balances reasoning and brevity as the token budget increases.